Well, good morning. My name is Jeff. I'm with the machine learning team here at Unity. I get really excited to talk to you guys about some of the interesting stuff we're doing at Unity. A lot of people know we actually do a lot of machine learning, a lot of it under the hood here at Unity. And there's kind of a topic I'd like to talk to you guys today about around what we describe as behavioral engineering, using a product we call machine learning agents. And we'll talk about what that means today. Before we begin, how many are here are like just pure game developers or like to create games? Okay. Well, what about machine learning guys? Are machine learning engineers? Any machine learning folks? Aspiring machine learning people? All right, cool. And just kind of everything in between. All right. So again, if you think about like machine learning in games, and you think about some of the advancements in deep learning, deep reinforcement learning, you hear all these topics around AI. Actually, a lot of it starts with games. A couple examples here. Anybody in here play Dota 2? Okay, some Dota players. So Dota is a really difficult game. There's competitions in the world, and OpenAI actually created agents and bots inside of the game that actually beat some of the best players in the world. So they hosted a competition about a month or so ago, but literally created using machine learning, able to beat the top 10 players in Dota 2. Go. Anybody play Go? Any Go players? Yeah, Go's a really hard game. I'm a really beginner at Go. Really difficult game. And DeepMind actually solved Go, and there was a Netflix video about it. And Go was one of those problems where when IBM Watson solved the chess game, very iterative, big bang approach. Solving Go in that way really didn't work, and so they had to use a lot of new techniques, which kind of spawned a lot of the thinking in AI. But everything starts with in these worlds in gaming. And so today I want to talk to you about how we're actually taking some of those research pieces and actually trying to bring them back into the games. So I'm heading the product side for our machine learning agents product. It's actually an open source repo. After this, you can go and download and kind of play around. Integrates with Unity. We have Unity SDKs and Python SDKs, all around creating agents inside of games, and agents actually being driven by machine learning. And all of this notion around behavioral engineering, how do we drive, either characters in the game or the game itself using machine learning. And we'll kind of talk about a little bit what that means a little bit later in the presentation. So this is sort of the workflow for machine learning agents. You can set up the game for training, you can train the agents, and of course you embed them into the game. So set up the game, you train it, and then you put it back in the game. So before we actually begin, let's just hash out a definition. So what are agents? At a really simple level, agents are just something that inside of your game that actually performs some sort of action. Now, it could be a tank, it could be a player, it could be a tree of anything inside of the game. All an agent is, it just takes an action inside of the game. Now, at any moment in time, any frame, the environment is in a certain state. So, for example, the tank drives out, there's a bunch of enemies around. In that frame, that's what the state looks like. And from the state, the agent actually collects an observation. So you're in a tank, it sees all the enemies, it sees the terrain, it sees all these different things. And the agent actually is collecting observations every frame as well. And so from these observations, agent takes an action. And this action is actually control what is called the policy. And the policy is actually the really key component in using machine learning and deep reinforcement learning inside of games. So you have an agent, sees the state around it, takes the observations, and then the policy tells the agent what to do. And we'll talk about how do you actually create this policy to drive certain behaviors inside with your agents. So if you think about what are agents and how can they be used in games, the way we kind of think about it is once you can create an agent inside of a game, there's kind of three types of ways that you can kind of leverage it. The first one is what we call the player agent. So if you think about the agent is at the point of view of the player. So the agent actually plays the game as you, the human, from that perspective. The second is what we call the non-player agent. Now, the non-player agent could be non-player characters. It could be like your sidekick or the enemy trying to shoot you. But agents can also, can be used, around for the sort of non-player characters. And the third one, which is actually sort of a little bit more far-fetched, is what we call the invisible agent. So the agent can actually be the game itself. So if you think about it, the game takes actions based on what the player is doing, what the state of the game is, what other folks are doing. So it's really kind of advanced stuff. So if you can think about a game that just sort of morphs as the player plays the game or things change inside of the game. So some of the kind of practical uses in a player agent, we think about it from a game testing perspective. If you can create an agent that plays like a human, maybe you can run through the game and sort of do a lot of testing. From the non-player side, you can actually create new kinds of adversary opponents, new sort of companions, new sort of like characters that typically in game AI is fairly challenging to do. And of course, in invisible agents, we think this is where you can actually do really dynamic difficult tuning. You can do things like like new kinds of player engagement that are really purely machine learning driven. So if you can create an agent to play a game, these are sort of the kind of vision of uses we think you can take with agents. So how does this kind of work under the hood? So if you think about your Unity scene, you have several agents, right? Again, an agent could be anything inside the game. You have this brain, and the brain is actually what controls the agent and what holds the policy for each agent. So if a tank is moving down the street, should it turn left? Should it turn right? The brain is actually what dictates that movement for an agent. And then we have Academy, and Academy is actually really just like a wrapper for us to communicate with Python. Now, inside of like training, especially in machine learning, most training frameworks are written in Python. And of course, as you guys know, most games and Unity, of course, is written in C#. There's a lot of C# scripting that happens. So what our Academy does actually creates an external communicator between the Unity side and also the Python side. And these are actually, on the left side, these are actually just game objects inside of Unity. So you sort of just drop them in, and you just kind of incorporate it pretty straightforward. So now that you kind of set up the game for training, now we're thinking about how to train the agents. Now, folks who have done some machine learning know that training is more art than science. There is definitely a lot of ways to train agents, and that is sort of the secret sauce on how you drive the right kind of behaviors for agents inside of games. So we think about it, and there's two kind of methods. There's reinforcement learning, which I think in the machine learning side you hear a lot about it, and then we have something what we call imitation learning, which is predicated on something called behavioral cloning, and we'll kind of talk about and show some examples of how they both work. So reinforcement learning, agents learn through rewards. So if you think about us as humans, you touch a hot stove, over and over and over again, you're going to stop touching it, right? You just learn through these like negative and positive rewards not to do something. The way it kind of works is through a lot of trial and error. Just go over and over until the agent figures out the optimal policy. The simulations can be sped up greatly. So most of the time when we do training for games and reinforcement learning, we do the time scales up like hundreds, and running it like several hundred frames per second. And what comes out of it is an agent that has what we call superhuman abilities. And through this sort of method, you can create agents that are just unstoppable in the game. And I'll show you guys a video that kind of illustrates that. So just kind of quickly recap, in reinforcement learning, you have an agent, it gets some observation, it gets some reward, it takes an action, and this is over and over again. And over time, as you can see, the agent sort of explores the world and eventually figures out the best exploit strategy, and that's how the policy gets developed. So really just the basic kind of workflow of how reinforcement learning works, and in the context of like Unity games and agents. So we'll show you an example. Any of you guys ever played Frogger before, like some of those crossing the road kind of games? So this is really basic examples. So in the observation, the camera is actually looking at the pixels inside the frame. The actions is that the chicken can go left, right, up, and down. And the rewards are, every time it gets hit by a truck, it gets a negative reward. Every time it picks up a gift, it gets a positive reward. So really this, we didn't tell the machine how to play the game. We just gave them this really, really, really basic set of like, I guess, what is good, what is bad, and what it can do. And we'll show you kind of how that works. There we go. So before training, as you can see, the policy is telling the chicken just to kind of randomly move around. So as you see, it doesn't really know what it's doing. Picks up, gets hit by a truck. After 1 hour, it starts to kind of figure out how to play the game. So you can see, it's starting to learn. Still gets hit by a truck. Not perfect. All right, now after 6 hours of training, now you see the chicken just unstoppable. So you can see, it doesn't take long for these more simpler games to actually figure out how to play. And really, this is just want to illustrate that at a very basic level, this is what reinforcement learning is all about. It's allowing these agents from the, again, from the perspective of the player to really beat games at a superhuman ability. Now, most people cannot play the game, unless you're the top Frogger player in the world. You're gonna have a lot of difficulty sort of like recreating this. And so if you can actually create agents that can do this, there's a lot of interesting practical applications. So that was reinforcement learning. The other one we think about is what we call imitation learning. Now, this is a little bit different where the machine actually watches a human play, and then after maybe, let's say, a few minutes, it actually learns how to play based on just watching, the human player. It's a lot of it's basically done in real time. So you're not like in reinforcement learning when you're running at thousands and thousands of iterations. You're really just a human's playing it, watching it in real time. And the difference that what comes out of this from an agent perspective is that it has human-like abilities. So reinforcement learning, we saw the chicken, it was unstoppable. But in imitation learning, the agent actually sort of behaves and plays like a human. And I'll show that with a quick example. So this is a game called Anti-Graviator. And what you see, so what you see on the left is the human player, and what you see on the right is the machine. Now, as you can see, the machine, after a few seconds, still hasn't quite figured out how to play the game. But over time, you'll start to see, right around 25 seconds, it starts to kind of understand how to play the game, watching the player on the left. So at this point, after only 25 seconds of watching the player, the machine actually learns how to play this game. And this is just sort of the final view. As you can see, it's almost unrecognizable. This is about 20 minutes of watching. So as you can see, the machine on the right and the human on the left, it's a little bit hard to distinguish which is which. So that's really the basic, again, it's a very simple example to show sort of like the possibilities you can use with something like imitation learning. So this is just kind of summed it up. We have reinforcement learning and imitation learning. And in the MLAgents toolkit, which again you can get on GitHub, provides a lot of integrations to how to do this in any Unity-ANZSEA Unity game. So again, wanted to kind of bring it back to that inside of the MLAgents toolkit, we actually provide a lot of different examples. Now they look really simplistic, but mostly just to kind of, and it was sort of intentionally done this way, just to kind of strip out all the graphics, strip out all the cool physics stuff, all the stuff you saw in the keynote, the rendering pipelines, really just to kind of get down to the core sort of like, like base of like what you need to kind of illustrate some of these techniques. Again, they all have a certain reason that we created these examples. They showcase either advancements in the research side for machine learning, and we'll kind of illustrate some of that later. And just to kind of showcase the different kinds of games, different kind of examples. As you're thinking about this in your game, how can you incorporate? So we'll run through a few of these examples today. The first one is our 3D balance ball. So this is actually the first environment we just kind of designed to use MLAgents. So if you think about these platforms, the goal is to keep the ball upright. In the observations, the agent can really just see the platform orientation, the ball displacement, and the velocity of how the ball is moving. And the action is really just to rotate. And the reward is if the machine can keep the ball up, it gets rewarded. And over time, it eventually just figures out never to drop the ball. So to show a quick video of that. So this is actually a fully trained model. This takes about 15 minutes to train. So as you can see, we didn't code anything. We didn't, write any actions or scripts. This is really just a machine trained model, keeping the ball up and balanced. The other thing that we want to introduce is this concept of curriculum learning. So one of the things that's interesting, especially when you ask machines to sort of learn tasks, is that sometimes it takes a long, long time for a machine to figure out how to do something. If anybody has taken calculus or taken really advanced math or really advanced literature courses, you don't just learn calculus. You don't just pick up a calculus book, you read through it, and you just know calculus. Nobody, unless you're some crazy freak genius, can learn calculus this way. So in a lot of ways, a lot of this stuff is kind of modeled on how humans learn. So when you learn calculus, you first learn arithmetic, 1 plus 1, 1 plus 2, and then you learn, division, and then you learn algebra, and then you eventually get to calculus. And so the way we think about it is that in certain scenarios, when you're trying to train an agent to do something, if you don't give it sort of the scaffolding of knowledge of how to do smaller, simpler tasks, it may never figure out the really advanced stuff. So curriculum learning is a really, really interesting area of research in AI about just how do you sort of like create really intelligent agents, and it's really modeled after how humans sort of learn, any kind of subject. So just show a quick video. Again, this is just a very simple stripped down example. So as you see, the agent is trying to like figure out how to jump over the wall. Now, the first thing it kind of learns is how to jump over a smaller wall. And it sort of like figures out like how to move things, and you can see like different sizes of the walls. As you're training it, what happens first is that it just first learns how to move the block around, then the smaller wall, and then the bigger wall. And it eventually figures out how to do the really more advanced tasks. So the other environments we ship is what we call multi-agent soccer training. So this is also another very interesting area. So a lot of the examples I showed today were just really single agent problems. You have one agent, nothing around, and just has to solve a problem. Now what happens when you have two agents? Where you have other agents or other characters or other objects in the world that the agent has to learn how to interact with. It could be in a cooperative sense, and it could be in a combative sense. So we created this thing called a multi-agent soccer training. Now, for folks who have played soccer or know a lot about soccer, you usually have offense, you have defense, and when you put them together, they have to work together to figure out a common goal. And so again, it's a really fascinating area of research that can be applied to games. Most games have multiple agents. So in this case, in this video, so the agents train how to play offense first, and then they play how to play defense, and then you put them together with a common reward, a common goal, and they try to figure out how to play together. Now, again, this is a very simple example, but it just showcases like this area of machine learning where you have multi-agent needing to, do, in this cooperative sense, beat the other team. And last, I like to illustrate, we actually just shipped this in our latest release for MultiAgent, so we call curiosity-driven exploration. So what does that mean? So if you think about like really, really huge open world games, and sometimes like there's like one task you got to do. Like you got to go through all these different things, you got to jump all through these hoops, and you got to get this key, and you got to go to this door. Now thinking about that from a machine learning context, that's a really, really, really hard problem for an agent to figure out. So how do we actually solve that? So there's this concept of like what we call curiosity-driven exploration. So in some ways, there's an intrinsic reward, right? So we actually tell the agent, hey, if you actually just spend some of your time, maybe 10% of your time, just looking around, just being curious, kind of like how we are. We get curious, we kind of read something, and sometimes we discover these epiphanies. So in the same way, we actually kind of teach the machine to do the same thing. We give it some reward that gets rewarded for just doing some curiosity, and usually it can solve these really, really what we call sparse reward spaces in a really fast way. So I'll kind of show two videos on that. Whoops, sorry. Can you go back? Oh, actually, no, that's right. So let me just kind of describe the environments real quick. So there's 9 rooms in this environment. There's one switch, and there's 6 stone pyramids. And you have to hit the switch first, and then you got to go back and hit this other block, this gold brick, and that's how you go to the next level. So this is the video that shows how it works without any curiosity. So this is just, after, I think this is something like, I think about 20 hours of training. The agent still really can't figure out how to solve this game. I mean, it's just running around, doesn't know what it really needs to do, and doesn't know it needs to hit the switch. And this is a lot of training. I mean, this is 20 hours, trying a lot of different parameters, and this is the best outcome we can get without something like curiosity. Now I'll show the video where we actually enable curiosity, the same amount of training, and so what you can see is actually the agent now figures out that it has to hit the switch first. It hits the switch, okay, now it knows, okay, that if I hit that, give me something nice, and then it goes and finds the actual reward to get to the next level. So again, same problem, same environment, almost the same amount of training, but one just gives a little bit of reward just on curiosity. And again, if you can see, this is what we call a sparse reward space. There's just a big open world, and there's just a lot of things that can happen, but it has really only one major outcome. It's going to get it. There it goes. This video is a lot longer than I anticipated, so we're gonna watch the agents stumble through this a little bit more. But again, if you can apply this to like a much larger open world game, you can see that like if you're trying to train an agent to play bigger games, you need to apply sort of different kind of like techniques in the training side. And so those are just a few of the examples that we have in the MLAgents toolkit. Again, if you go to our GitHub page, we have a pretty massive community of researchers, game developers, trying it out. We have issues. If you have an issue form, please send us anything there. Again, tons of different examples in joints and motors and 2D games and all kinds of good examples. The last part I want to talk about is, okay, now that we train an agent, that's great. We can train an NPC that plays against us. How do you actually put that back into a game? Also another very interesting and very difficult problem. So machine learning inference is really the action that the model takes. So you have a trained model. We train the agent. You put it in the game. So all inferencing is like, what do we ask the model to do at a certain amount of time? Just to give you kind of just a general idea of how much complexity is in inference, this is just a really basic MLAgents model. There's 26 matrix optimizations for every few frames. So there's 6 multiplications, 4 inner products, 16 element-wise operations. And of course, these agents need to run at 60 frames per second. So inside of a game, you're competing for resources for CPU and GPU. So when you have to add inference on top of it, and again, inference is the process of passing a bunch of data into the model to make a decision. It's a really challenging problem, especially on like iPhone devices, mobile devices that have power, all these different environmental constraints. And of course, at Unity, we support all these different platforms. So if you want to have a machine learning model with the agent, work on, let's say, the PlayStation 4, Xbox, iOS, that challenge becomes very, very complex if you're trying to sort of take this approach to designing certain elements of the game. So I did want to actually, I'm kind of happy to announce that we're trying to solve this problem with our Inference Solution. So what we want to provide is actually just a generic platform-agnostic API that allows you to use both CPU and GPU inferencing. And what I mean by that is like smaller neural networks, you want to use the CPU because you get a lot of efficiency. Larger, really dense networks, you want to leverage the GPUs because it's much faster. And so our inference solution sort of understands the context of the model and able to sort of provide the right type of inferencing. Of course, it's optimized for platforms. As you may or may not know, all the devices like in Apple, Samsung are actually trying to create dedicated neural network chips. So a good example is the Apple, new Bionic chips are leveraging the DPS processor just to actually do the inferencing. So what we actually want to take is actually leverage the hardware pieces. So when you're a developer, you don't need to do all the integrations with all the different platforms. You just sort of call this generic API, and we kind of take care of all the inferencing on the hardware side. And of course, we have fully integrated with MLAgents. Our aspiration is to allow any developer to bring any kind of machine learning model. If you think about in the AR space, you have a lot of object detection, object recognition models that you may need to bring in. And so our aim is to actually have an inference solution for anyone wanting to use neural networks inside of games. So this is Puppo. Puppo's sort of our mascot, sort of like 12th teammate. So Puppo is actually a corgi that we use sort of to illustrate some of these concepts, actually putting inference inside of games. Puppo, all the joints and motors are actually all machine learning controlled. All the limbs, the only thing we code a very, very light game logic, and most of the walking and how it needs to run is actually determined by the machine. And so in this game, I'm going to show you, we call it it's a Puppo fetch game. So it's actually, usually I will show it on my phone, but I'm having a little bit of the technical issue, so I'll show the video version. So this is Puppo. We throw the stick, and it actually goes fetches. Now you see how it's running in all those joints. We didn't write any of the physics or anything to how to do. We really just told the machine, figure out how to run, and we gave it some rewards. So it's actually pretty cool, and this is actually running an iPhone device, actually running, pretty smoothly. Again, this is just a screen capture from an iPhone device. But again, it just kind of illustrates that hey, you can actually put the model today into very simple games. Next one. Now, what happens if you actually have more than one agent? So how does the performance take a hit? So we have another demo called Puppo Goes to the Races, Day at the Races. So we have one, he's just kind of trying to get it. Now we add 10 more, cute little corgis. And as you can see, the inferencing, is still pretty, about 1 millisecond. And so just going to show the illustrate, you can keep adding more and more agents, and our inferencing kind of will handle a lot of the, like really, really difficult pieces. So this is all actually open source as well. You can go to our Unity blog, check it out. You can, we've seen people modify Corgi, a Puppo to do, be this really either even more cute or really crazy looking. So all of this is open source for you to go kind of try around, and you can actually build either through Xcode or through Unity onto iPhone or similar with Android devices as well. Also want to talk about our labs team. So Unity has a pretty experimental labs team. They're actually building an inference engine that works across all platforms. One of the challenges with inferencing and running machine learning models in game is that, especially in Unity games, is that cross-platform support is still really difficult. For us to try to integrate with every device, try to leverage every piece of hardware can be really, really difficult. So what the labs team is actually doing is creating a cross-platform high-performance implementation of an inference engine. It's actually leveraging some of the components in Unity today, like the burst compiler, the ILO2 CPP, and of course, like a lot of the Unity compute shaders. And the reason doing that is because actually inferencing on machine learning models is basically just a lot of like matrixy math, which is really similar to a lot of the concepts in graphics. So they're able to leverage a lot of these similar concepts to create like an inference engine. And the reason we want to do this is because, for example, if you want to load a game on Xbox today, Xbox actually does not have a lot of libraries for machine learning models. You can't load TensorFlow models. You really can't load any kind of models in Xbox today because the libraries aren't there. And Microsoft may support it in the next generation of their Xboxes, but today those libraries don't exist. So how would you, if you're an Xbox developer, put inference on a console like that? So this is where this kind of project, like an inference engine, comes in. So this is Jelly Bowl. It's by a studio called What Up Games. So What Up Games is a very indie studio based in Seattle. And they were experimenting with MultiAgent. They came up to us like, hey, we're shipping this indie game in Xbox, through the Xbox One program, which is their indie program, Xbox ID. And they asked us like, hey, we trained all these MultiAgents to do these cool things, but we want to put it on the Xbox, and we don't, really know how to do it. Can you help us out? So we actually were able to incorporate the lab's inference engine into their game, into an Xbox console. And I'll show you the quick demo of that. So this game, the aim is you'll see these little balls are trying to grab these small red dots and actually score it into their actual respective homes. So this is actually running on Xbox. And all the players in here are actually all AI controlled ML agents. So you see they're trying to battle, they're trying to get it. But again, this is running on the Xbox. And if you wanted to run it on like a PC or Mac, it's pretty straightforward. There's a lot of stuff out there today. But running it on the Xbox is fairly difficult. So this is actually using the lab's inference engine to actually control the behavior and actually run it on the device itself. So that's actually it on my end from the presentation side, and I want to leave some time to answer any questions. Again, github.com/unitytechnology/MLAgents. We're one of the top 20 projects for AI, both on the research side, but also from the game development side. Any questions, please email us at ml-agents@unity3d. Our team is always interested to hear more about any issues, always willing to help out. And of course, we have a lot of our thought leadership, all of our blogs, all of our posts on unity3d.ai. So with that, we've got about 10 minutes or so. Happy to answer any questions or any thoughts or any comments from the audience.